Okay, so good evening, everyone. Okay, so welcome to this third lecture. So first, I'll make some announcements, and then we'll get to the material. So first thing about group formation. Okay, so some of you have emailed me saying you're finding it difficult to find groups. So how many of you have already formed groups? Essentially, these are supposed to be study groups. Okay, so most of you have formed groups. If the size is not the optimal number, which is 4, then try to get some new people. There are some people who are still lagging behind, so get them into your groups. Or people who have not yet formed a group, try to seek out during the break or after class and form a group. It's mostly for your for your studying. So you want to kind of make use of the group to enhance your understanding. If it's not helping you in that way, then don't worry about it. You can always do the assignment by yourself as well. It's not too challenging, so you can always ramp up. Okay? So that's the first thing. And the second comment is, as you saw in the last lecture, I'm using a lot of notations, right? Compared to a typical business class. So the idea is, of course, to learn everything from the ground up, and I've been telling you this from day one. So try not to worry too much about the notation. So basically, if you're fearful about the notation or the math, it's not, it's just it's just a language to express what you know about modeling. In this case, machine learning models. So it'll help you. So we're going to ramp up, and in lecture 2 we already saw some notation, and in the subsequent lectures we'll kind of reuse the notation. So in subsequent lectures, hopefully we'll not have too much new introduction of notation. But in the long run, this is going to help you, and the teaching staff is here to help you. So meet me after the class, during the break, online or during the office hours to learn this material. Okay. And since your view has to be pragmatic, I mean, you probably have taken some of these. Maybe some of you have taken data mining course, so you already know some of the material. So try to fill up all the gaps so that your foundation is solid by the time you exit this course. Okay. And so assignment 1, you have to submit it as an R Markdown file. So it's just an R file with text, usual regular text. Don't worry about Markdown formatting. It's quite minimal, but it's not important. So think of it as a text file where there are parts of the text file where you put some tags. Okay, and you'll see. Hopefully, maybe during the break, I'll open up a web page that shows you where you can include the code. So that you can open that file in RStudio or something like that, and I can run your script, and you can also develop your script, your solutions that way. Okay. Yeah.
Each group has one report, or
yeah.
One of us?
So each group has to submit one report. So try to decide among yourselves. Don't submit more than one. It's only because we know that in the group you're gonna communicate and know the solution. So there's no point replicating the same thing again. Okay. So. Yeah, and I guess last time I tried to. So I'm gonna. By the way, people who are trying to copy what I write, I mean, you have the notes here. So whatever I write, at least you have it. And things that I'm verbally saying and you think it's important to write down, you can write down. Okay, so don't try to match paste with what I write. I mean, unless my handwriting is completely illegible, then you can definitely write. Okay. So let's look at the. So this is the same slide deck that I had shown to you guys before. So I'm going to continue adding a slide hopefully every lecture. So for this one, I guess we are in lecture 3. So okay, so So I'll tell you today's goals and again actually revisit where we are heading. So it looks like, at this point, since it's the third lecture, many of you may be thinking, oh, I'm learning A, B, C, and D, but I don't know how they're connected to each other or how they're connected to the larger picture. So I'm going to spend some time on that. But before that, let me just clear what are the goals of this lecture. Okay. So today we're going to try to understand this notion of bias and variance. Okay. Variance is something that you have heard of. If a random variable will have a mean value and it will also have a variance, right? So we'll revisit that. Variance is something that you're familiar with, and we'll also talk about bias and in the context of modeling. And you'll see that actually, a very top level comment is that neural networks lie on the side of very little bias but very high variance. So they can actually overfit, but which means that they'll overfit. But in practice, it looks like they're not overfitting. Okay, it may be because of some other issues. So it's something important to know about so that you can understand where neural networks fit in the picture eventually and where linear models can and fit into the picture. The second goal is how to change the bias and variance. So you can potentially, you cannot change the bias and variance of a single model, but you can think of a family of models, and we'll talk about what is meant by family of models. And we can talk about, okay, if I change something about, look at a subset of this family of models, then I can have a certain type of bias. If I look at some other part of the models, maybe I'll have a different type of variance. Okay, so at least that's the intuition that we need to gain. The third point is something just to connect the dots with some of you who might have seen about linear regression modeling. There's things like hypothesis testing, whether the coefficient is significant or not, and so on. We'll see that it's quite limited, but we'll see the example. We'll probably recap these things in a in a clean way for a particular linear regression model. Okay? There are many linear regression modeling assumptions and inferences that you can draw given the assumptions. So we'll look at one clean way of what assumptions did we make, what is the linear model, can we do hypothesis testing, and if so, what does it mean? Okay, so that's what we'll get to. And the fourth part is, which is kind of the most important part in this lecture, is going to be use of cross validation. So you should be very clear about why are we doing cross validation and where all is it applicable. Okay, so with that. This. Here. So last week, actually, I was a bit hurried towards the end, and so I want to kind of just revisit the last part of last lecture, which was I was talking about. So I was talking about KNN, right? So let me recap what I was talking about. Um, so this is lay of the land, and then lecture 2, basically. So this is what I'm going to try to do in the first few minutes. In the meantime, any questions so far? I sent a lot. I said a lot of logistical things, but any questions? No questions. Okay. So to figure out, so I'll spend a few minutes explaining the first point, which is that first thing I'll do is try to repeat what I said in the. I mean, not repeat the concepts themselves, but what did we do in the first lecture? What did we do in the second lecture? Right. So, does anybody remember what did we do in the first lecture? No. Notation. So if you don't remember, that's fine. We'll go back to, at least the goals, right? So understand. So what is supervised learning? That's roughly what we saw in the first lecture. what is meant by linear. So in the first lecture, linear model meant something because linear corresponds to a linear transformation and comes from this linear algebra foundation, right? And the third point was able to use vector notation. That was the notation part. And the fourth one was what is the KNN classifier actually doing? It's not summarizing the data. It's literally keeping the training data with it. And every time a test point comes, it finds the nearest neighbors and looks at the average y values corresponding to them and outputs them, right? So that's the first one. And in the second lecture, we looked at what is the best regression model. So we had this thing of expected square prediction error, right? So we started with regression. So regression means let's say we are predicting a single outcome. So y random variable is one dimensional and it's numeric. So we chose least squares loss, the residual sum of squares equivalent to squared loss, and we tacked it on with the joint distribution between x and y and defined this expected square prediction error, right? So given that, we figured out what is the best regression model, and then how KNN and linear models are kind of approximating this best regression model. So that's what we did in the first bullet point. And actually, let's go to horizontally. So the next point was what are these best models? What are this best regression model? What is the best classification model? We figured that out by just working with the joint distribution of our random variables, input and output random variables. Then we said, okay, in classification, there's a nice interpretation, which is the Bayes. Wow, is it shutting down? Okay, it's restarting. So we were looking at this Bayes classifier, the notion of a Bayes classifier, and Bayes decision boundary. So we understood what a decision boundary looks like for two-dimensional data, and essentially two features and two classes. So we could draw a boundary between the two classes if they were like well separated, essentially, right? Okay, the projector is going to turn back on soon. The third point was, okay, so we understood what are the best regression models and what is the best regression model, what is the best classification model. Then we went back to the KNN, okay, because we want to, it approximates this best regression model as well as it approximates the best classification model. So we want to understand why is it not enough, right? And so that's where I think I didn't do a good job, but I'm trying to say that when the dimensionality of your data, which means not the number of observations, but the number of but the number of features increases. Let's say you have two features. That's what I was drawing on the board. Instead of two, think of 200. But you can't really imagine that. If there are 200 features, then the notion of neighborhood is drastically different. So in two dimensions, you can kind of see what is the neighboring point. In 200 dimensions, it becomes very difficult to figure out what is a neighboring point to a test point. Okay. So to kind of motivate that, I will get back to that neighboring point business in a minute. Uh, and then the last part, which I missed, fourth bullet point, was that what are these relatives, as in other families, other models which are related to the k nearest neighbor that we saw and the linear model that we saw. Okay, so I'll get to that in 2 minutes. But before that, let me finish the lay of the land. So why are we starting with KNN? Okay, that's the first question. Why are we looking at linear model? Right? Why are we looking at a joint distribution between x and y? Why are we looking at a joint distribution between, for example, the qualitative variable g and y, right? What was the use of this particular criteria, right? And and I guess this dimensionality aspect was kind of clear that KNN falls short because of dimensionality that I'll repeat pretty soon. So why did we start with these objects essentially? Uh, is because if you look at the course structure, I mean, if you kind of look at the syllabus, first the first part is essentially about supervised learning. Okay, and supervised learning, the bucket of supervised learning involves lots of methods, uh, starting from simpler things where you can understand what's going on in terms of from data to the model, right? And for that, we started with KNN and linear models. We could have started with any other model. For example, a popular choice could be decision trees. Right? Decision trees are very easy to motivate and understand how data is influencing the construction of the model. Right? We could have started from there, but we started with this because we wanted to start with some elements, some members of the supervised learning family of models, and motivate how it's related to the statistical properties of the data. Uh, so so we started with two methods, and in fact, what we're going to do in the next few lectures is just focus on linear models. Okay. In fact, we're going to forget KNN from today onwards, and just focus on, let's drill down and understand what's happening with just linear models. Okay. And then we'll get to supervised learning itself, but nonlinear models. Okay. So think of something called support vector machine uh, with something called a kernel. Then it becomes a nonlinear model. Okay, and we'll figure out what is the nonlinearity of that model, and not just that, things like decision trees are actually nonlinear models. So that's why we want to kind of start with things which are all linear or have the same core idea, and then get to things where they're exactly the opposite, where they're not linear anymore. Whatever it means, they're going to be nonlinear. So SVM, random forest, decision trees, they're going to be on that second blob. Okay, and then and then the last part would be unsupervised learning. Okay, unsupervised learning we'll get to where it's a completely different workflow where we don't have labels for your data, so you don't have a target to predict directly given to us. You can always assume some target and do something else, but that's a tangent. Okay, so here your objective is to just understand your data. Okay, whereas the first part of the course is mostly about not just understanding your data, but also to create something that can be used in production for forecasting and therefore making decisions and so on. Unsupervised learning can also be used to make decisions, but this is like finding patterns. Okay, it's more closer to, I guess, data mining. And in between these three blobs, we'll also sprinkle a few other things, like what is the connection to something called maximum likelihood estimation. Okay, because likelihood as a term is essentially what likelihood is nothing but a conditional probability, and so we'll figure out. We've already introduced the joint distribution pretty much. So likelihood is just going to be a function of that. I mean, like a conditional probability of something given something. So we'll sprinkle likelihood relation to maximum likelihood estimation. We'll also sprinkle maybe a time series analysis into the mix, and so on. Okay, so that's roughly the lay of the land. Uh, any questions about what we're doing in the few lectures is kind of doubling down on this linear models inside supervised learning. Okay, and we're understanding every property, every direction that we can probe this class of models. Okay, what is meant by linear? How well does it work? Can I vary the bias and variance of this class of models? What does linearity mean for regression? What does linearity mean for classification? These are all questions that should come up in your brain, and you can ask it during the class, as well as you'll see. Over the next few lectures, you will be more confident in understanding this part of the model, model zoo pretty well. Okay. So that's the lay of the land. So now let me come back to things such as referring to in lecture 2, which is the uh, first part was about dimensionality. And I'm going to repeat the same idea, but hopefully this time it will click, is that let's say so now what I'm going to do is change problems. So my first problem, let me just number it as 1, is going to be a one-dimensional problem where my feature is only 1. Okay, it's only one feature. So let's say the feature value is between 0 and 1. Okay, the feature only takes a value between 0 and 1. I normalize it by its max value, so it's only between this. Okay, and it's positive. Now, so dimensionality and KNN. Let's say uh, I want to find a neighbor for a test point. So my test data point would still be a one-dimensional feature, right? For which I want to make a prediction. I'm not showing the y values here, but I want to make a prediction for that thing which I wrote it as x. Okay, that's the value. Maybe it's 0.05 or something. Okay. I just want to figure out what is its neighborhood in this one-dimensional space. Okay, this is all the feature values can only take values on this interval, and I want to figure out a neighborhood. So, and that's what I'm defining. So let's think of a neighborhood for this point x over there, and a neighborhood here is that length. Okay, that length. So actually, neighborhood size and feature range. Okay, there are two words that I wrote there. What do I mean by that? Neighborhood size is what is that interval which I'm thinking about. So I want to think of neighborhood as like an interval in one dimension, and in general in higher dimension some sort of a volume. Okay, some sort of a ball or something which covers where this particular test point is the center, and there's a volume around it. Okay, so neighborhood size, let's say, is I want to take neighborhood size to 1/10. I can just choose any number. Let's say I want 1/10 of the. So why is it? So why is it a ratio? So I just picked a number between 0 to 1 to say that this is a percentage of the whole volume of the feature space. Here feature space is just 0 to 1. So what is the 10% part of this feature space? Okay. So I want to say for that point x, I want to find neighbors who are within the 10% part of the feature space. Okay, that's all these, all these guys here, all these guys here, right? All those guys. There are many points there, but that's a bunch of points which are in in that neighborhood. Okay.
So have you seen a black person yet?
I don't think so. You can come back at 7:30 when we take a break if you want. And what is the second column is feature range, where I'm just saying that okay, to get a neighborhood size of 1/10, what is the range of feature values that I'm looking at? Okay, and the range of values would also be 1/10. Okay, for example, 0 to 1/10 or 1/10 to 1/20th, sorry, 1/10 to 2/10, and so on. So whatever that length. So this is essentially what I used as side length. By side, I was just meaning the support of the feature, which corresponds to that neighborhood size of 10%. Okay, this is I guess 10%. Now in 2 dimensions, so now think of a second problem where I have 2 features. Okay, so 2 features, both features are between 0 to 1. So that's why I can draw it as a box where every point in that box is a pair of feature values. Okay, so think of now a test point x. I want to say, okay, I still want to think of this test point x and a 10% neighborhood around it. Okay, so what is 10% neighborhood around it? Since it's this is square. Let's say this is x1, x2. Okay, this is a 10% neighborhood around it. And I'm asking what is the so let's say that shaded region is 10%. Okay, so neighborhood size is still 10%. And I'm asking what is the, so both features are between 0 to 1, let's say. I'm just asking what is the support, or what are the values that x1 will take, what are the values that x2 will take for this neighborhood. Okay, I just push the neighborhood to this corner, but think of, if I had point that cross test point somewhere else, then I would think of like a box around it, and I'm just asking what is the support, or basically the values that x1 would take in that neighborhood, and what is the values that x2, that feature, would take in that neighborhood. Or what I'm saying is, if I had a X here, I would think of a 10% neighborhood. I'm just asking how much is this, how much is this, how much is X1 and X2 is varying in that neighborhood. Okay, and that is basically 1 by 10 square root, right? Because in 2 dimensions is basically 1 by 10 side times height, okay, width times height. So similarly, you'll see in 3 dimensions it's going to be 1 by 10 to the power 3, sorry, 1/3, right? And in general, maybe 100 dimensions, it's going to be 1 by 10th to the power 1 by 100. Okay, so this number is actually 0.999, let's say. I mean, it's actually close to 1. That's what I want. And these numbers are in between somewhere. So all I'm trying to say is that for the same neighborhood range for a test point, which is like 10% of my whole feature space, I'm actually per coordinate, per feature value, I'm actually looking at all possible, almost all possible values that each feature will take. It's like saying, okay, the neighborhood of a point in 100 dimensions is, think of all points where every coordinate is between 0 to 1. Like that's like every point, right? Anybody missing the link? Yeah.
1 by 10 to the power n, that's the feature range, and 1 by 10 the value, that's the other value, right?
Yeah. So neighborhood size, I'm keeping it fixed. 10% of the volume, 10% of the feature space. I mean, essentially the volume. So features are, let's say, all features are between 0 to 1. Okay, for simplicity, right? They're always between 0 to 1. They're between 0 to 1. So I'm just saying, I'm going to think of neighborhood as like a 10% volume around any test point. Okay. You have to be proportional, right? You can't shrink the neighborhood when you go in higher dimensions. Something you have to keep fixed. Either you keep the side length fixed, then the neighborhood will shrink, or you keep the neighborhood size fixed, and the side lengths will increase.
Yeah, but I will go till a point where I can find the first nearest neighbor, right? So
Sure.
So if that point is in the, you think of the shaded region, if my point is there, so I'll cover whole square, right?
Yes. So, okay. So his question is, okay, what does this have to do with the algorithm? Because the algorithm is going to pick, somehow figure out the distance between this test point and every point, and find the nearest, k neighbors. That's what the algorithm is. K nearest neighbor algorithm is. But this discussion is not. So far, I've not told you the algorithm. So the algorithm depends on the notion of neighborhood. So I'm just thinking of how does neighborhood change as I go into higher dimensions. So think of this in other words. Think of points uniformly spread in that feature space. So for example, uh, like between 0 to 1 in the first one-dimensional problem, maybe there are points which are like every 10, 0.1 units apart. Okay, so you can figure out, okay, there will be a bunch of points in the neighborhood of that shaded region. Similarly, you can spread points here, like equispaced points. Then you can see that there are more points in the neighborhood range. Okay, but that is fine. But we want to kind of fix the neighborhood size as the same. Okay? Otherwise, you're saying we'll change the neighborhood to be smaller. So if I change the neighborhood size to be really small, then I'll have the same number of points as if I had in the first dimension, in the one-dimensional problem. Maybe in this problem I had 5 points in this. Okay, equally spread out. Let's say there were five points which were captured in this range. If I want to keep only 5 points captured in this range, I'll shrink my neighborhood. So, but that is a characteristic of the algorithm. I'm just saying that if you want to keep the proportion volume, so the notion of neighborhood the same as you increase dimensions. Okay, that a neighborhood is something which is like 10% around this test point. Then the neighborhood kind of looks bigger and bigger in the sense of per feature, this guy keeps increasing on each axis. Okay, that's all. So, how does it affect KNN? KNN will just do, it's a procedure. You can still compute neighbors in high dimensions, except that from this intuition, it looks like in high dimensions every point is a neighbor, because if every point belongs to my 10% neighborhood range, okay, or whatever percent, I can put 5% or whatever, right? Every point belongs to that neighborhood range. So I should, I cannot discriminate between, okay, everything belongs to that neighborhood range. Which one should I pick to, make my prediction, right? So that is the curse of dimension. You can always, okay, I can always shrink my neighborhood range and pick something, but that means, I'm being extremely sensitive, right? So, so I'm shrinking my neighborhood definition, right? So that means I'm extremely low. It's as if I'm saying at this point, if I had any data point, then that will be my prediction essentially. Yeah.
Is this always the case when we're using X dimensions to make a prediction, or is it the case we happen to have, let's say, 10 variables in the file?
Yeah.
Does it still hold true, or what if I use only a selected number of variables?
Yeah. So his question is something to do with practice. So if I already have 10 features, do I have to worry about KNN on that 10 feature data, or can I subset and pick a few features and then KNN will work fine? You can always do that pre-processing. If you have a tabular data and you have lots of features, maybe even you made it categorical. So sorry, if you convert categorical to one-hot encoding, then you'll have too many features. You can always drop some of them which you think are uninteresting.
So this is just concerning the independent variables, then, right?
Yes, this discussion is only about independent variables. So what is the space in which we are working with? Or to put it simply, KNN has two things, right? K, which is fine. I can pick some number of neighbors, 20 neighbors. The second thing was distance, and distance is the thing which is connected to this notion of neighborhood. Okay, distance in high dimensions. These points are, in that case, all those points which are like spreading all over the region are actually within the 10% neighborhood. So that's like a counterintuitive idea that it's like saying that they're within 10% neighborhood range of this point, although the distances may be whatever the Euclidean distance that you compute, right? So that's the connection between neighborhood and distance. Okay, so it takes some time because you can't really imagine more than 3 dimensions, so that's why it's hard. But all I'm trying to say is that there are too many points if you think of the same neighborhood size as you grow the number of features. Okay, that's all. Yeah.
So in how many dimensions does this start to break down generally?
So it won't break down if you have if you have like 100 dimensions, but you have a billion observations, then it will not break down, because then you can actually shrink the neighborhood size. So as you were saying, KNN by itself will not think about, okay, even if I have 100 dimensional data, I can still figure out, I can always compute distances and spit out some solution, right? The solution quality would be fine if you have lots of data. Okay. You can choose K big enough so that there will be enough points even if you shrink the neighborhood range. Okay. That's so the idea is, in this part there's going to be 10% of the points of the whole part, right? So that's why I was keeping the same 10% as I was going to higher dimensions. And in 100 dimensions, this if you have the feature lengths on each side about 0.99, are essentially covering the whole feature support value between 0 to 1, then you'll have 10% of the points. Is kind of the idea. So to get 10% of the points, I'll have to increase the each feature support all the way to 0 to 1 essentially. Okay.
How do you understand that the algorithm has broken down and it's not working? Like 10% is okay.
So you'll not have 10% points. So if you pick so the algorithm is picking K, so let's say 20 points or 50 points, then you're just making decisions on those 10%. Then your neighborhood size is extremely small essentially. Okay. So
how will I judge what how will I come to know
so it's basically, yeah, so you cannot figure out so if you're asking whether can I figure out the performance of the algorithm based on this, you can, in the sense of your algorithm will be significantly worse because it's a local algorithm, right? It's just looking at, okay, at this test point, what are the neighbors and what is their predictions, and I'll average it. Okay. All I'm saying is if you take 20 points in 100 dimensions, it's going to be corresponding to a really small neighborhood. So it's not, so it's like saying I'm going to look at an extremely minuscule neighborhood of this point. Okay. That's like a high variance, I guess, model. which may really do well in test and it will do really bad in training. In test. And we'll get to that variance business in 2 minutes. So in practice, the consequence of if you have high dimensions, you can run KNN, it will perform badly. Okay. So now we want to understand why it performs badly is because you can always run the algorithm, but it's looking at a really, really small neighborhood range. You can always pick 20 points, which are closest, but it's not really a neighborhood, or in the sense you have changed the definition of the neighborhood. As you increase dimension for the same number of points, you are decreasing the neighborhood. Okay, so it's like saying I'm considering lesser and lesser number of points to inform my decision. Okay, do you understand? So if you keep k fixed, as you increase the dimensions, I'm considering lesser and lesser number of points to inform my decision. That will make my decision or my prediction unstable in a sense. That's roughly what's happening. But we'll see actually in terms of bias variance trade-off by actually we'll see how k influences bias variance trade-off pretty soon. So you'll see that low k implies high variance, which is what I was talking about. When you increase dimension, keep the k fixed is essentially a high variance. But anyway, we'll actually describe it in detail in a few minutes. So don't worry if you didn't understand the last part. Is this fine? At least just in terms of intuition about why KNN may fail. So my second thing was so last time we saw KNN and I guess a cousin, a different model which was like KNN, where I was saying that instead of taking the average, right? So I'll use some notation here. So instead of taking the k size neighborhood, I guess. So it's a little bit messy notation, but what I'm saying is take the average of all the y's, where this notation just means it's an indicator, just means it's going to take a value 1 when xi is in the k neighborhood of the test point, and it's going this guy is going to take a value 0 if not. So it's just a way to say, what is KNN doing? It's just saying that I'm going to take average of yi's, but I'm only going to take those yi's where the corresponding xi is in the k neighborhood, or just this is a k close enough to this test point. Okay. Now last time we saw that instead of this indicator function or things which take 0 and 1, I can actually change this to a function which I think I used the letter k. I guess alludes to the kernel function, but it doesn't matter. So it's just xi and x test. You see this function, this indicator. So what is an indicator function? It takes a value 1 if the condition inside the square bracket is satisfied, this square bracket, and if condition is not satisfied, it's 0. Okay. So that function is taking a value 1 or 0, depending on whether xi is one of the k neighbors or it's not. Okay. Instead of that, I made a different function where the inputs are the same, xi and xtest, because see, xi is a part of the evaluation, right? Xi and xtest together tell me whether that function is equal to 1 or 0, right? This function, the one in which I put in a square. So I'm gonna make a different function which I'm gonna call k of xi comma xtest. It's just sort of like an inverse distance. For example, think of it as an inverse distance where I'm saying if xi is extremely far away from xtest, then maybe this function k should not be suddenly become 0, but it should be like maybe inverse of the distance or some such like that. Okay, where I'm saying I'm willing to take the average of all the yi's, but I'm gonna downweigh the yi's which are like extremely far away. I mean the xi's which are extremely far away, their yi's I'm gonna multiply it with numbers which are really small. That's all. So and then there has to be some normalization. So instead of 1 by k, there'll be a sum over this k functions. Okay. So this is I guess an example of another model. This is also a model. This is also a lazy model. It's not really modeling anything. Given that k function, and literally given the k function, it makes a prediction. That's it. Right? There's nothing else. There's no knn of the k. There's no k part. But this is a model which is related to the knn, so it will have the same type of properties. Okay. What is this model called? I actually don't know. It's a kernelized version of knn, probably. Yeah, in the notes it just says. We just say. We just say kernel method, but it's basically there's no name. Yeah. So what's an example? So I'm going to give you another example of a relative for a linear model. So what is a linear model? It was like something like beta transpose x, where x is the input variable, could be p-dimensional. So this was a linear model. So instead of this, here is a example related function. It's going to be, so what is beta transpose x? It's just beta 1 times x1 all the way to, let's say, beta p times xp. We have p variables. Instead of that, you can have a function which is beta 1 times some function of x1 plus beta p times some function of xp. So what are these functions? All I'm trying to say is that this is also a linear model, but it's just semantic difference. You can think of f1 of x1 to be like a log of that original x1 value. So let's say x1 is always positive and greater than 1, then you can take a log of that. Maybe it's maybe it's some count data. Then sometimes it's worthwhile to take a log of that value if you want to kind of change its scale. Or you could take maybe xp instead of, maybe this function is nothing but xp squared. Maybe this function is nothing but log of x1. This is just an example of another linear model. It's basically essentially the same as linear model. All I've done is transform the variables individually, right? There's a name for it. What is it?
Feature engineer.
Yeah, applying these functions is feature engineering. But here we are not. These are pre-decided in the sense that you pre-processed it, and then learning the model is just finding the betas again, right?
So that in the case of skewed variables, like if your data is very skewed, then you go for the log scale or something.
Yeah, potentially. So these transformations, it depends on domain expertise. These are, I guess, a name for this. I guess a less used name for this is called. It's essentially a linear model, but the method is called a dictionary method, where you kind of consider many such functions and you kind of drop off some of the functions when you actually run the model. Okay. So anyway, it's essentially the same as linear model, but I just added some complexity by saying, okay, we can transform the features, transform each individual feature. Okay. Any questions? So this was a simple example, so that's why I guess I ran out of time last time.
What do you call this again?
In the note I've mentioned it as a dictionary method, but that's because people think of, okay, I don't know what transformations to make, so let me think of all simple transformations I can make for each input. So for each input, I'll make a log transformation, an e to the power x transformation, a square root transformation, x squared transformation, and so on. So maybe 5-10 such guys. Then for every input feature, you'll have 5-10 such transformations. Then you don't know which one is the correct one to actually make the prediction. So you'll drop some of the elements. So you already have a dictionary of these transformations, and you're dropping some of these transformations that you don't care about when you actually train and learn a model. So that's why it's called a dictionary method. But
So actually, if we are using this method, then we are blindly relying on only a data, and we are not using any of our intuition to come up with some relation.
no, the choice of these functions is your prior knowledge. Right? So your question is, if we are blindly applying these transformations, then we are not. We are relying only on data to tell us whether these transformations are correct or not. That is true, But to come up with this initial candidate of transformations is where you do essentially feature engineering or domain knowledge information is captured here.
I'm a little bit confused. I thought previously we tried to find the beta coefficient and then by applying them on the data we got the
Yeah.
model which is F.
Yeah.
But right now it seems you have the F's and what are you trying to find?
Oh, these are just instead of F's, I should have written it as G's. We're still trying to find betas. It's the same as linear model. You should not be confused between these two. Essentially the same as linear model. I just did an initial pre-processing of the input variables. So think of f1 of x1 as some other new feature variable, and fp of xp to be another feature variable. And then once you do those transformations, you can ignore these f's, and it's still a linear model problem. So it's still a linear model in the new transform space. Okay. There's nothing going on. It's just to intuit that okay, this is not very different beast from this guy.
So that would give you kind of a shortcut to model like logarithmic data.
Yeah.
And so at your end result, you would just exponentiate it, and you have what you were supposed to be predicting.
So here we are only transforming the input variable. So your question is about whether we have to do an inverse transformation. So these f's are some transformation of the inputs. It may or may not be necessary. So far we have not seen anything to do with making a transformation and taking an inverse transformation. We'll actually see something about generalized linear models later on. So I just wanted to at this point say that okay, KNN, there's something like a KNN. For linear model, there's something like linear model, which is essentially a linear model except for a transformed input. So at this point, that's the narrative. Later on we'll see what is the relation to generalized linear modeling. That's good. Okay, so now actually I'm going to start the third lecture, and today's goal is essentially to try to understand two things, two major things: bias, variance, I guess trade-off. I guess in between I'm gonna, since I'm as an example, I guess we can go through linear models again, and then the second part would be cross-validation. And so how are these two topics connected? If I want to change the bias and variance, I'll use cross-validation procedure, which I'm going to describe towards the end of this lecture, to change the bias and the variance. So first, let's understand what is the bias and variance of a model, of a different model. Okay, maybe for each model there's a bias and variance aspect. There is, and then we'll figure out how to kind of change this bias and variance numbers. Okay, if you change the numbers, you'll get different models. So we'll use cross-validation as a tool to move between different bias values, different variance values, and so on. That's essentially what cross-validation. I mean, that's essentially what we'll do with cross-validation. But there is more story to cross-validation anyway, so we'll get there. So okay, so last time I had this picture where I had a line segment, and I was saying, okay, so linear model and KNN. Okay, it doesn't have to be on the extreme ends, but maybe linear model is somewhere over here, KNN is somewhere over here. So this was in the first lecture. Towards the end of the first lecture, I was saying, okay, I drew just a line and said somehow linear models are more biased, and KNNs are less biased. Okay, so I just offhandedly, said that okay, this is less biased, that's less biased, and this is more biased. Okay, and that's what that remark I made in the first lecture. Now let's understand what is this bias and what is this variance, or what is the bias of a model. Okay, so to do that, we'll again ignore data. Okay. we'll ignore data, but we'll bring in another beast. So let's see. So remember there was this EPE definition, right? EPE was a criteria which only relied on the joint distribution between x and y, right? And it was like basically the expectation of y minus any model squared, right? Something like this. Now, what if my model is determined by data? Okay. What do I mean by that? So here, if I give you a model, you can tell me what the EPE is if you know the joint distribution, right? So to get this EPE score, which is this expected prediction error score, you need two things, right? Somebody has to give you an F, and somebody has to tell you what the joint distribution is, right? Joint distribution between x and y. If somebody gives you those two things, you can tell me what the EP score is by just computing this, right? But in reality, we actually the whole problem of supervised learning is to get this F using data, right? So let me call that F hat. Okay. So similar to think of beta hat. Beta hat was something which was determined using my data, right? My data matrix and my y values, right? So similarly, I'm going to use F hat for that. And what's going to change is that now F hat actually depends on data, whereas I want to think in terms of expected score, right? So F hat depends on data, and I'm going to use just for temporary reasons, I'm going to use a notation tau to represent the data, which means in fact, I'm going to use because I don't really want to specify a specific data set. Okay, I want to say each row of my X matrix is also a random variable, and each entry of my Y matrix is also a random variable. So that's why I just made them capital letters. The only difference with the actual data and this guy tau is that now these are all random variables. So there are n random variables. Okay. Think of like 10 random variables or something. Let's say n is 10. It's kind of irrelevant. 10 pairs of random variables. So 10 xi's and 10 yi's. Okay. In addition to the x and y which is there in this expectation. So this expectation already has two random variables, which is x and y. Right? I've already used them up. But I'm going to also say I have 10 other xi's and 10 other xi's, x's and 10 other y's. Okay, those are random variables. I'm just going to use the shorthand notation tau because I don't really care about the specific. I don't want to use the notation. This is kind of not very important, but tau is actually just this. Tau is just a collection of these random variables. Okay. Then my EPE for this F hat depends on tau. Okay, so this F hat therefore is also a random variable. Okay. So I just made for if you had a specific data, that would be that would make this guy, something like little x I and yi, right? So this would be my data set. If I had this, I would get some model F hat. I'm just saying that if I don't have a specific data set, some other, a generic data set, that's why I made the component of this data set random variables, then I'll have a generic model, which is a random model now, essentially. Because it's derived from data. I mean, we haven't told how it's derived. Let's say it's linear model, then we know how to derive it. But all I'm saying is, given this data, there is a model that you can get. So given a specific data, you can get a specific model, let's say linear model. Given a bunch of random variables, you can get a model which is a function of those random variables. Okay, that's all. All I'm just making the data, anonymous in the sense that each row is now not a specific bunch of numbers, but a random variable. That's all. Then my EPE, I'm going to say, okay, if this guy is random, then I need to take an expectation with respect to all the randomness in this model as well. Okay. So my expectation will be with respect to P of xy, and also with respect to the distribution governing these guys, these x, capital Xi, capital Yi's. So sometimes, I mean, it's a shorthand to write tau there, and then the same thing, y minus f hat tau of x squared. So what changed from this line to this line? I changed f of x to f hat of x, f hat tau of x. Okay, that symbol f changed to f hat of tau. Okay. It's just a change, but what is the f hat of tau? It's actually depends on the data. So that's why I took an additional expectation with respect to tau. Tau is a bunch of random variables, right? It's a collection of like 20 random variables, 10 xi's and 10 yi's. So I just took an expectation with respect to that. This is actually called the generalization error. And we'll understand, how is this related to bias and variance. I'll immediately, I'll tell you in the next slide. But this is just to motivate, like, this is an error. Once here it was any arbitrary function, I couldn't compute the EPE. But now I'm telling you, I got some data, and then I gave you a function. Then you should tell me the error, but you should take the expectation over all the possible realizations of the data, right? Like, see, in our case, data is coming from a joint distribution, which is a joint distribution between x and y. So if I get the data once, then I'm basically drawing from this joint distribution. Maybe let's say capital N is 10 there. This n is equal to 10. I'm drawing 10 times from this joint distribution. So I got a specific pairs of values of x and y. That's this guy over here, and I got a model. If I drew again 10 times from the same joint distribution, I may get different data set, right? And from the different data set, I'll get a different model, right? So this f hat of tau is like the random model. It could be this model, it could be that model, depending on what data I drew from the joint distribution. Okay? That's all. That's another way to interpret like what's happening here. All I did is from here to here, I just added a tau, which is an expectation over the randomness in my data set. Okay. Yeah.
And based on distribution of data, we can generalize some sort of models. Like because here.
So this is asking. So what does EP is asking? For any model, tell me how will it perform on my data, right? So how will it perform on my future data, which is not given. So I've only told you what is the joint distribution between x and y. So for any model, so let's say it's not. I just tell you, okay, linear model with beta 1, beta 2, beta 3, all ones. You can tell me what the score is because you know the joint distribution. You can tell me how it will perform in the future in expectation. That's what this is, right? Now this guy is saying your data can change every time, because there's joint distribution between on your input and output. Your data can change every time. I'm going to take an expectation with respect to that and then tell you the performance of your model. If the model doesn't depend on data, then there's no point of this expectation. If the model is any fixed model that I decided a priori, ignored the data and decided a priori, then there's no this tau business. It's the same as this. Okay. Tau only comes because I'm going to use data to estimate a model. I haven't told you which model. It could be a linear model. It could be something else like an SVM and so on. But yeah.
For introducing these random variables, we don't need to know the distribution that we are taking.
The distribution is exactly P of x comma y. Right? Our data always comes from so that's why this whole discussion doesn't really involve data as such, specific data set, no numbers anymore. This discussion is saying my data always comes from a joint distribution between x and y, input and output variables. That's P of x comma y. Okay. My data always comes from here. So if I have n observations, these n observations also come from this joint distribution by sampling. Somehow you get a realization from this joint distribution. Right? So let's say some number of them. Let me call this tau. Based on that, I figured out a model. Right? I figured out a model which depends on the tau. That's why I'm calling it f hat tau. And I want to find the performance of this guy I can find the performance, but it depends on a specific tau, specific realization. So I took an expectation with respect to tau to average that out. Because every time if the data is coming from a joint distribution, I can draw different realizations of data every time I get every time I sample from it, right? So there's that variation. I'm just squashing that variation by taking an expectation.
So basically you're saying that you get the data from the joint distribution of x and y.
Yeah.
Between those random variables, yeah, that one.
Yeah. So there's a pxy from which you get these guys. You also get these guys.
Yeah. So suppose from that data you're getting 10 xi's and 10 yi's.
Yeah.
And based on different data points, you can get 10 different models. Suppose 10 x's and 10 yi's.
Yeah, you can get different guys like this, right? Yeah. Your samples could be different. And therefore you can get different models. So the first, let's say you got a realization, n sample realization, 10 observation realization from your data from pxy, that may correspond to a specific model. Some other 10x observation realization from your data may correspond to some other observation, some other model. Sorry.
Depending on f hat. Like what?
Yeah, f hat is going to change based on the data, right? You will decide. Let's say you think of a linear model, then you will decide the model based on the data, the actual realization. So it could be different based on the actual realization that happened. It's a little bit non-trivial. Think about it. That I'm thinking of now not a single data. In practice, you will have a specific data set. You can't really change it. But I'm thinking of a joint distribution on this input and output random variable, so I can generate all sorts of realizations of data. I can have multiple copies of data, and they can be different. And so I'll get different models. So I'm averaging them out. Okay.
Is a joint distribution, is that the same thing as a conditional probability distribution or mixed probability distribution?
No, joint distribution we discussed last time. So the question was, what is a joint distribution and how is it related to a conditional distribution? So a joint distribution would be P of x is equal to x, comma, y is equal to y. It's like, what are the values, what is the probability of x taking a value little x and y taking a value little y jointly. That's all it means.
Okay.
And a conditional distribution means, given that I've told you that x takes a value little x, what is the probability that y takes a value little y? That will be different. It will be like P of y is equal to y given x is equal to x. They are related, but let's not worry about that. Yeah. So, okay, why did I go to this definition of why did I get to this definition? This is called a generalization error, and let's actually make it simple. So let's not keep the capital X in this previous slide. So this capital X is a generic random variable, right? So I want to say, okay, I don't care about in general what the EP is. I'll tell you what X is. Okay, only on that particular X value, tell me what is the expected error that you can see. Okay. So that is going to be X EP of X naught. It's just some specific test point. On that test point, just tell me what is the expected error given this joint distribution that you know. Okay, this is going to be again expectation over pxy and tau of y minus f hat tau of x naught squared. I mean, given x is equal to x. That's what this means. So actually, this should not be. P of y given x is equal to x naught and tau. Essentially, I'm saying that I'm specifying one of the values to be exactly x naught. Now this is a conditional probability. Y given x is equal to x naught. So we're gonna try to look at this guy, and to even make it simpler, what I'm gonna do is, let's assume that in reality, y is related to x in this way. So in reality, there is some f true. So that the f true notation is not in the notes, but I'm using it here to kind of keep things clean. Plus epsilon. Okay. So okay, I'm using Greek letters here and there, but just think of if you don't like epsilon, just use some other alphabet. Doesn't matter. So this is assume. Okay. Let's say there is a relationship between x and y, which is that given an x, there is some unknown, way to get to a y value, so some intermediate value, and then I add an epsilon. What is that epsilon? Epsilon is, think of epsilon as a random variable whose expectation is 0 and the variance is sigma squared. So I defined some as a variation of EP in the previous slide, and now I'm saying, okay, let me specialize. First step, specialize it to x naught, because I don't care about many, in general, all over the expectation. I want to fix it to a specific x naught rather than thinking about an expectation about x as well. And then saying, okay, now let me think of the relationship between x and y to be some fixed value. So it's some fixed function which takes an x, spits out a value, and then I add a random number, and that random number is such that its expectation is 0 and its variance is sigma squared. If you want to keep it concrete, think of that epsilon random variable to be Gaussian. Okay, Gaussian with 0 mean and variance sigma square. Gaussian is just a normal random variable with mean 0 and variance sigma square. Okay. So given this, if I make this assumption, so then the EPE of x naught can be decomposed into 3 terms, and I'm going to expand this term out right here. It's going to be equal to sigma square plus f true of x naught minus expectation over tau of f hat of tau of x naught square. I'll just write it out and then explain what each term means. Plus, this is the third term below. Expectation Okay, now it looks like there are too many symbols dangling. So what is, why are there so many terms? Why did I even expand this out? Okay, so let me just define what these terms are, and the expansion, I don't think it's just gory and we can do it, but it's not intuitive. So let's focus on the intuition. So what is this? So under this assumption, I can actually break down this guy that I defined in the first line into 3 parts. Okay, this part, and this part. Okay, so the first thing that I circled is called the irreducible error. Okay, it's like saying, no matter, give me any data set. Okay, because this guy is 0 mean, if you give me a data set, maybe my f hat can approximate this guy, f true, right? Can make, can figure out what f true is. But even if you know f true, you'll always make an error because there is a plus epsilon. Okay, it's like saying, okay, what is another way of saying this? Let's say somebody told you this is, I'll give you what the f true is. You don't really have to do anything with data. What is f true? I'll tell you. Somebody told you that. Still, you can't predict y. Well, because you can predict y with some error, and that error is because of epsilon. Because somebody else is adding some noise and saying that. So you predicted y is equal to 10. Somebody else because I gave you that f true, and f true is telling you that for that x there is a y value is 10. But then somebody else is saying, okay, the 10 plus some additive noise, which is that, for example, think of a normal random variable, then maybe it becomes 11. Then your prediction is always going to be different from the ground truth. So that is this irreducible error, and you can see that. I mean, even if I told you this, you will always make this much of error. So there is no predictable in the system at all, because this is random variable. So every time I draw a y value, I get this guy evaluated, and then some random values added. So that's irreducible error. Is it clear? Okay. The second term is called the bias. Okay. It's called the bias of the model. Okay. What is the model? The model is always f hat tau. Okay. When I say model, it's f hat tau. That's what we got from data. It's saying, okay, f hat tau could be different based on different data sets. Let me look at the average prediction of this model. Okay, there will be different models based on different data sets, but let me average all those guys, right? That's expectation over tau of f hat tau at that given test point x naught. Okay, that's the average prediction that I'll make over different realizations of data sets. Okay, how far is it from this guy f true? It could be off. For example, f true could be like a parabola, a quadratic function, whereas what if my f taus are all linear functions? Okay, given an x, maybe it's 10x. Given an x, maybe it's 11x, 11 times x. Whereas this is x square or something. Then there will always be an error. Okay. So that's this bias at that given x naught. Okay. So there is no ambiguity here because there is nothing random here. First of all, there is no. I mean, you have taken the expectation with respect to tau out. So this is a fixed some constant. There is some fixed constant. There is no random thing here because this is some unknown true fixed function. Right. So this is called the bias, or bias, square of the bias. I guess bias squared. That's the bias. And then the last term is called the variance of your model at a given point x naught. So to understand the last term, it's kind of easy. Yeah.
Tau is dependent on the n, that's how many you are sampling.
So tau just represents the data. Like you have 10 copies of your data, like 10 observations in your data. Then there are 10 random variables corresponding to xi's, 10 random variables corresponding to yi's. Remember?
So
Tau is just a short form for, instead of writing this huge thing, I'm just writing tau. Instead of huge thing, I'm writing tau.
So you said it was fixed, right?
No, if you draw a sample, then it's going to fix,
And
right?
the other function that we just saw.
Oh, this guy is fixed. That's true. So I just said assume my data is such that given x, this is how it transforms, plus some additive, randomness, which gives me a y.
So you're subtracting the fixed true value from the average prediction.
Yeah, that is called the bias of your model. And you forget about these two terms now. Now this guy is just the variance of your model at that point. And in fact, there's no need to write this, very ugly expression. I could have written it as something like expectation over z. Let's call this whole thing z. Okay. So z minus expectation of z, the whole square. This is just a definition of the variance, right? So variance of a random variable is nothing but take the random variable, subtract its mean, square it, and take its expectation. Okay. This is just a definition of a random variable. So at a given test point, f hat of tau is a random variable. Depending on the data, there's going to be different predictions at that point. Right? It's just saying, there is a random variable, subtract its mean. Maybe I should put a bracket there so that it's even more clear. So there's a subtract its mean, square the difference, and take the expectation with respect to the randomness, which is z. So I just use another placeholder just to show that it's if you don't like this notation, it just means some sort of a variance, okay, at that prediction point at x naught. So we just decompose this expected square prediction error into a irreducible error, a bias, which depends on the f hat tau, and variance which also depends on f hat tau. Depends on f hat tau in the sense that which model class I pick, for example, a linear model or KNN or SVM or random forest or neural network, that's going to influence how much this difference is and how much this difference is. So for example, if you use a neural network here, that f hat tau represents a neural network, then for pretty complicated f true, which means that pretty complicated curves relating inputs and outputs, the neural network may very well capture that curves, the relationship between input and output. If it does, then its bias is extremely low. But on the other hand, its variance is going to be extremely high. Okay. And we'll see an example through KNN. So with neural networks, it's not clear why the variance will be high, but with KNN, we'll see why the variance will be high or low. Okay. We'll work through that example right now, but this is a general form, just to kind of understand how bias and variance are. Yeah.
Could you tell us one more time the conceptual difference between the first term and the variance?
Yeah. So the first term is the difference between two fixed numbers. Okay. So first number.
No, I'm sorry. The first term, which is the I don't know what the symbol is. The irreducible error and the variance.
Oh, this is the irreducible error.
Right.
Yeah, this is the variance. Yeah, this is also a variance, but it's the variance of a random variable, epsilon. Okay. Because I said epsilon is a random variable with mean 0 and variance sigma square. So we haven't shown how we got from here to here. Okay. Under this assumption, the moving from here to here under this assumption requires a lot of mechanical expanding the brackets, substituting the definition of expectation and all that messy thing.
So it's essentially they're both variants. The first term and the third term they're a variance, but that's a variance. The first one is a variance that would be impossible to capture
Get rid
by
of.
a model.
Yeah, to get rid of. Yeah. You cannot capture. Yeah, precisely. So you cannot capture it in your any modeling, and therefore you cannot get rid of it. And so your error will at least have this much additive component in expectation.
Okay. And the third term is a variance, but it would be possible to capture that. You just have to have the trade-off between the bias and that variance.
Yes.
Maximized.
Yes. So the third term is a variance due to the model class, like linear models, KNN or whatever. The first term is due to what I assume the relationship between x and y is. Under this model, this type of decomposition holds. This is just for us to understand. How, if you did not have this, then you can have dropped this, and you would have just a bias and variance. Okay.
The third one is actually due to variation of data, right? It's not the model.
This is a variation due to data, yes. And if data varies, the model varies, right? F hat tau varies. I'm just saying. Okay. Think of f tau f hat tau is like a linear model class. Okay, in the sense that I'm only thinking of betas, but I don't know which beta to fix. Depending on every tau, I'll figure out which beta, right? I know what how to get a linear regression model is. But this is just saying that at a given test point, for every different type of data set, I'll have a different models, right? Because data cannot be the same, so model is different. And so I'll have different numbers here. So that's why this is a random variable. I'm just subtracting the random variable from its mean and taking the square. So this is the variance of that model at that prediction point. Yeah. Is this clear? Okay. So actually, now is a good time to now ground everything. Now, so far it's been like, oh, there's so many symbols going on. So let's fix this, and for that we'll do one simple exercise. Okay, we'll take the part which is easy to do, which is let's find the variance of a k and n model at a given test point. Okay, I didn't write the third term. This is nothing but the third term in previous page. At a given point, some model like KNN model, really you don't have a choice except for the k, right? It'll have a certain variance, right? And the variance is with respect to the tau thing. Okay. So what is this? So what is this variance? So f hat tau at x naught minus, okay, actually, let's keep it simple. So let me write a simple expression for the KNN model. I keep changing the notation all the time, but so 1 by k sum over L is equal to 1 to k of f oops, f hat let's call it y L. It's not a good expression. Oh my god. So I'm going to use the remember there's an expectation of, okay, let's actually do, so let's only focus on this term, this, let's find this guy which I circled, this expectation over tau of f hat tau of x naught, for f hat of tau is a KNN model for simplicity. And also we'll assume this, okay, which is that y is f true plus epsilon basically, okay. Okay, so since y is f true, let me just put f true of xl plus epsilon L. So why did I write this? Ideally, I'm supposed to write some y yl where L is equal to 1 to k, where those y's are corresponding to those x's which are the k closest to x naught, right? I just want to find x1 to xl. I'm just indexing them as, let's say x subscript 1 is the x subscript 1 to x subscript L, sorry, not L, but k are the k closest to x naught. Okay. I'm just indexing them as xl. So just think of it, my test point was x naught. What should KNN first find? K nearest neighbors. Okay, there will be some points, right? With some indices. I'm just calling those guys x1 to xk. Just saying the sub-index to, if you don't like this, you can put a bracket there saying this observation was some index, but it is the lth closest to x naught. Okay. But this is yi. This is yi, right? Yi. Right. We assume the model to be this.
But that depends on x naught, right? Why?
Yeah. X1 to xk are the k closest to x naught. Yes, it depends on x naught. Yes. Where? I guess I didn't write where. This is clear. Right. Now, if we take the expectation of this guy, with respect to data, right? So, which means that this actually is supposed to be capital X. Okay. Yeah.
Why do we have the e to the l term there? Haven't we pulled that out in the original formula from the previous page?
We have. No, we have, but I'm just saying that. Where is this? Remember, there is the x capital I and y capital I. These are the data points, right? So these two, right? Generic data points. So I'm just saying that under that assumption, under the assumption, yi is nothing but f true of xi plus epsilon. I guess I'm just going to use I. Okay. So my data point is nothing but f true this plus epsilon I. So I'm just trying to say what is yi, right? I'm saying for a generic data set tau, there will be a corresponding yi's, there will be corresponding xi's. I just want to find the k nearest guys, and the k nearest guys yi's are just this, right? I just whatever the k nearest guys are, their yi's are this two terms. I just wrote the yi term. So this is just substituting the definition of yi here. We haven't done anything yet to the previous slides expressions yet. So if you average them, it's going to be sum over L is equal to 1 to k of f true of xl plus sum over L is equal to 1 to k 1 by k epsilon L, and there's also 1 by k here, right? So this is the and also what is the expectation of f hat okay, let me actually do it properly. So at x naught, f hat of tau is this. This guy, which I underline or putting a square. This is f hat at x naught, f hat tau of x naught. Its expectation is something I didn't compute yet, but its expectation over the data points is going to be dropping these epsilons essentially. So okay, expectation of tau of that f hat of tau at x naught is equal to 1 by k f true x, I guess, xl so all I'm saying is the expectation over tau, it just kills this epsilon else because epsilon is 0 mean. So expectation of something plus something, this guy goes away. Okay. All I'm trying to say is that the first term has its epsilons. That's because that first term is just a KNN prediction. The second term has an expectation, right? The expectation of tau still remains, but the second term, expectation of epsilons, goes away. Okay. And then there's another expectation. Not this guy, but outside there's an expectation. So all I'm saying is this guy will have some additional epsilons. This guy, because of expectation with respect to tau, those epsilons will go away. And then there's an outside expectation. I don't know how many of you are following this. Yeah. I can do it again. So yeah.
You're taking a regression example over here or classification?
So this is a regression example, but that's because I'm writing the way I'm writing this KNN prediction here. It's just the average of a bunch of numbers, right? And these numbers are nothing but yi's.
Should be integration.
Why? I'm taking the average of k nearest yi values. Just the one inside the block. Huh?
It's a continuous variable. yi is a continuous variable.
Yeah, yi is a continuous variable, but I'm not taking expectation. So I'm just first telling you what the prediction is. The prediction is nothing but this inside. Okay, this is my yi. Yi is nothing but f true of xi plus epsilon I or epsilon L, for example.
That is same as f hat which you have written over there because
This is f hat tau of x naught. This is f hat, not this. Sorry, this is f hat tau of x naught. So let me write it more cleanly. So what is f hat tau of x naught? Is 1 by k. I need to average k yi's corresponding to the xi's which are closest, right? So I'm just calling it as one sum over L is equal to 1 to k of some L closest guys, which will be f true of x naught plus epsilon else. Okay. Sorry, f true of xl plus epsilon else. Right? Any confusion with respect to this? Where xl's, just think of them as the closest to x naught. Okay, the test point. Okay, this is the prediction for a generic data. So that's fine. What is the expectation of over tau of f hat tau of x naught? Okay. This is actually equal to 1 by k. Sum over L is equal to 1 to k of expectation of f true of xl, right? Because this is the only part I don't know, expectation with respect to x. This is fine. I mean, the last part I just dropped out because that expectation is 0. Now take the difference, right? Take the difference. Okay, I have to square. Okay. Okay, so let's actually take a break.
I have done it.
Okay, so yeah, sorry for the quick break, but let's resume. So, okay, so I have a solution for this, which is you may not like it, but the solution is let's actually make x not random. So what do I mean by that? Which means that x's are not random. The only thing is random. The only thing which is random is y, and y is random because epsilon is random. Remember, y is equal to sorry. Right? I'm saying that in the relationship between x and y, I'm thinking of x as not random. So there is no distribution corresponding to x. Okay? Drop the distribution corresponding to x. But there is a distribution corresponding to y because epsilon is a random variable. So y is a random variable, and so y will have its distribution. Is a random variable. X is not a random variable. Under this assumption, it's kind of easier to work with this. So under this assumption, there is no expectation of x. It's just this guy. Under this assumption, f hat tau of x naught is 1 by k times this summation. So times the summation. Let's call it summation plus epsilon else. Right, and expectation over tau of f hat tau of x naught is also equal to just summation. Do you agree? I mean, where this sum, I just mean this sum. It's just 1 by k, that sum plus that was as before, except that sum, I'm just saying that if x is not random, that sum is some number, but it doesn't matter. Okay. And this expectation is also 1 by k sum, because we just saw that expectation in general is this, but if x is not random, this again this expectation is irrelevant. Okay. It's like think of xl's as fixed numbers. It's as if my data point is the x values are somehow not random, but the y values corresponding to them are random. Okay. Then you can see that the difference between these terms cancel. Right. We are slowly, we are doing it bottom up. First, we are saying, okay, what is this? What is this expectation? What's the difference between these two terms? Okay, the difference between these two terms is the one I underlined, this guy, and what is the variance of 1 by k, sum over L is equal to 1 to k of epsilon L's, where epsilon L's are random variables whose variance is sigma square and whose mean is 0. So what is its variance? I mean, this is essentially what the last term in the previous, I guess, this term, I just evaluated this, I just evaluated this, I took the difference, and the difference was just the sum of k epsilon L random variables with 1 by k in front. And I'm just saying that those random variables, if you square them, and so those random variables remain, but those are zero mean random variables. So its expectation is just going to be this guy. This is the final term. Okay. Is this a difference between these two? This remains, and I just want to find the variance of this guy. Is it clear? At least this variance. I mean, at least this term should be clear. Why is it the variance? Is only because I can write this guy minus its mean the whole square and take the expectation with respect to the epsilons, and that is just the variance. Okay, and this variance is nothing but sigma square 1 by k square times sigma square all the way plus sigma square k times. Okay, what is the variance? So variance of a constant times a random variable is constant square times the variance of the random variable, right? That's 1 by k square. And the variance of two random variables, variance of random variable x plus y is the variance of random variable x plus variance of random variable y as long as they're independent. Okay. So that's what it is. Variance of the first random variable L is equal to 1 is this. Variance of the L is equal to 2 is this, and variance of epsilon k is equal to that last one. Okay. Essentially, what I'm saying is this guy is sigma square by k. I mean, from here to there, it should be fine because there were k terms in the numerator and there's 1 by k square in the denominator. It's the same k terms. So k and k square get cancelled and there's one k in the denominator. But why is from here to here should also be clear. Variance of if you forget everything from this slide, but if variance of a bunch of random variables multiplied with a constant, you should know how to evaluate it. Okay, if they're independent. This probably is also covered in the probability primer, so have a look at that if you are confused. Now this part is just the difference between these two, and this is what the third term was. So all I'm trying to say is that the third term under this assumption is sigma square by k. So it has an inverse dependence on k, and which means that if k is small, then that term is generally large. When k is 1, that term is sigma square. But when k is 10, 20, then it's sigma square by 20. So as you increase k, you're decreasing this third term, which is the variance term. So as you increase k, you're taking more neighbors, so you're more stable, and you are not, you're more stable, which essentially is like an intuitive thing to say it has less variance. Okay. That's the connection I wanted to get to, but I made it too general, so that's how I was stuck somewhere. But I mean, basically, I did make an assumption here. It can be relaxed, but for today's, for this lecture, let's take this assumption. Okay. But anyway, so what was the whole point? Is that there is a bias variance decomposition for any model. So we looked at KNN's variance part. Similarly, KNN's bias is going to be, there's not much intuition for the bias term. It's just the KNN is going to take an average of k terms. So when k is large, then the bias is going to be, then the bias is going to be large. Okay. When k is large, then it's like you're taking the average of too many neighborhood points, so you'll not be able to meet if it's a quadratic over here. Whereas you're taking the average of a bunch of points, it's like it may not be a good approximation. Okay, that's what the bias term is. So when k is large, bias is large, variance is low.
So is that bias towards prediction or neighborhood?
No, bias specifically just means this.
I mean, in the context of KNN, so if the bias is large, Does that mean I'm predicting way too many points around or what?
Yeah, you're using too many points. I mean, bias is large when k is large, so you're taking averages of too many things. So you'll be you'll not be able to capture the fine-grained values of the like f true could be like bigly. If you take an average of a lot of points, then the average may not be the same as the prediction at that point. There's going to be a difference.
Like if it is a sine wave kind of thing, if you take a point on a sine wave, then
I mean, okay, so let's not bring in sine waves. So, I mean, that's a way to intuit it. I'm just saying that bias is just essentially this. So, if I have large k, then I'm too stable, so I can't really capture the curves in my prediction function. I mean, the f true is like all over, it's curving all over the place. If I take average of a lot of points, it's like a flattish. Like, think of it this way: if I increase k a lot, then I'm not able to capture the pattern in the data. I'm actually like fitting almost like a linear model, or literally a constant actually. And when k is small, I'm capturing the fine-grained part of the data set. So it's unstable. It's going to be, if the data point evaluated to something, then that's going to be my prediction. So it's going to be high variance. Okay. So high variance, anyway, we saw the variance definition here. I mean, the variance of that model at a given point is going to be sigma squared by k. Okay.
So that means when k is large, you are actually whatever values you're predicting, that would all be the same. If
K is large, yes.
that means it is like
Constant. Yeah. So that, yeah, go ahead.
I just have a more general question. So, I personally understand the concept of it, but I couldn't reproduce this math that you've just written there.
Yeah.
So, what level, just in general, what level of understanding are you asking us to get from this?
So this was to motivate bias variance trade-off for models. You don't have to understand. Okay, so you don't have to reproduce this, but you need to at least understand that there was some reason why I went from a step to a step. Okay, so this is never, I'll never ask, for example, in your exam and stuff. But this is just to motivate that a model can have a bias part and a variance part, and this equation essentially captures that there is, f true. Think of f true curves as to be f true curve is something like this. There could be models which may not be able to capture this data, which means that there is at any given x naught, let's say this is the x naught, there is this bias, okay, and the variance would be, if I have different data, if I had a different tau, so variance is going to be because of the realization of the data. So maybe for a different tau, maybe I'll get a different curve. Okay. So this is the first data set. This is the second data set. So variance is like the variation at that x naught around this dash lines. There could be multiple dash lines because of the different taus, different realizations of the taus. That's the variance, and the bias is just that no matter how much different data sets I draw, their prediction at this point would always be far away from the truth, only because the truth is too much bigly and the model is not capable of capturing that. Okay. For example, think of this as a linear model, then really it cannot capture anything. You'll just essentially have lines, like multiple lines. If it was a linear model, right? Like you'll have different lines based on different data sets that you get, essentially. But they'll always have some bias. That's this average of all these line values at this point minus the f truth is essentially the bias. Square of that is the bias square, and this variation around its mean value is the variance of that model at that point. That's as simple as that. So the derivation is not very critical, I would say. So it's mean value of all these, for example, linear models, mean values of all these linear models at a given point. Not the mean value, sorry, the variance of those points is the third term. And the mean value minus the ground truth is the bias, or the square of it is the bias square. Same thing. And maybe I should have started from here. Yeah. but experimentation. So okay, so actually, so I have quick quiz. So okay, if you've switched, then the people who have the other person's scripts just graded. We'll quickly go through the solutions now. It's not a big deal. It's just uh, if you have not been able to answer it, that's fine. Okay, so we'll go through the solutions now. Um, so so the people who people who are grading just grade according to if the answer is correct +1, if not -1, if nothing is given 0, just add it up and put it at the top. Okay. So what is the expression for the residual sum of squares? It's just sum over I is equal to 1 to n, maybe even 1 by n in the front. It doesn't matter, but yi minus theta transpose xi square. Right? Essentially, it's just saying sum of squares. So you have yi minus theta transpose xi. That's your data, right? That's the difference. Square of that difference is the error per observation. You're just adding the squared errors up, right? I mean, some variation of this is fine. Second one, can you use RSS to score a k nearest neighbor model? How many of you said yes? Yeah, be more confident. It's correct. Of course, you can always score any model with any criteria, right? I mean, it doesn't have to be. I mean, if you did not have squares, if you had absolute values, instead of square here, maybe absolute value of yi minus theta transpose xi, you can still do it. This is another criteria, right? You can just sum out I is equal to 1 to n. Okay. This is the absolute deviations criteria. Instead of squares, there is an absolute value. And you can always score any model. Doesn't have to be a linear model here. You can have a neural network there and you can still score that model. And so what is the regression output when k is equal to n?
Mean.
What is it?
Mean.
He's saying the mean. Yeah. So when k is equal to n, you're essentially saying I'm going to average all the yi's, which evaluates to something, but it doesn't change as your test point changes, right? So it's just so y hat is just going to be sum over I is equal to 1 to n of yi's. Right? I mean, you don't have to write this, but this is essentially what it is.
Could it have been any models output here, not only regression, but any models output could have been because because of the nearest neighbors and how it's covering all the area?
No. So this is the k is choice for the k is a parameter for just the k nearest neighbor model. So if you have a different model, it's not clear what the question even means. I'm just saying for k and n, if you choose k to be large, then it's like highly biased. Okay. So it's like saying I don't care about the input. I'm always going to predict a single number. Like let's say movie rating, it's always going to predict 2.5. Between 1 to 5 or something like 3.5. Doesn't matter what movie it is or anything. Yeah.
So, I'm going back to question
2. Oh, this is not the answer. This is just yes, I guess. That's not the answer.
So, the answer for this should be no, because if you use RSS for this, then you will run any optimization algorithm, it will be a non-convex optimization.
There's nothing to optimize. I'm just asking if you have a model. I've already kept, if I tell you the model, you have to tell me what k is as well. So maybe k is 20. I give you the model. Can you score it?
But again, the question is so RSS again, if you're talking, we can only use it when it's a regression problem. In a classification
Sure.
problem, you'll use a log linear method or something like that to score it.
Sure. I mean, yeah.
And even if in KNN also in regression, if you use RSS, it won't be a convex optimization.
There is no optimization going on.
But if you're scoring, you are optimizing it.
No. This is just RSS is just a score function. You can optimize it if you're finding the best guy. But KNN, I've already told you what k is. Maybe you can optimize for k, but then you can pick k is equal to 1, 2, 3, 4, and just evaluate the number, right? Evaluate this number. And the question is just asking, can you use a criteria like RSS, sum of squares, to evaluate a KNN model. You can evaluate RSS for any model, not just KNN. You can use any model. Some models, you can evaluate as well as optimize the model's parameters, okay, through gradient descent and all that. But that's fine. So I guess for the fourth question. So I guess I was looking for something like expectation of y given x. Just means this is what we derived, I guess, last time. Spent a lot of time on this. So if not anything else, this is the best regression model if you knew the joint distribution between x and y. Okay. And similarly, it's okay if you couldn't write this in time because the time was short. Similarly, if you have what is the formula for Bayes classifier? It's just the max over if there are k classes, I is equal to 1 to k. Yes, argmax of probability of g is equal to I given x. It's fine. Or x is equal to x, doesn't matter. So this is the prediction. So at a given point, find the highest probability mass class, the categorical value, and that's going to be your prediction. Right? So it's just saying, so at a given point, for example, on 2D plane, okay, at a given point, maybe it's 30% class 1, let's say it's class orange, and maybe it's 70% blue, then your prediction is just blue. Okay. So given the point, probability that it's orange is 30%, probability that it's blue is 70%, and then your Bayes classifier is just going to predict blue. Okay. That's the maximum of the probabilities at that point. There are two probabilities there. Whichever is the maximum, that's the point. If there are three classes, and whichever is the max of the three numbers, that's the class. Argmax just means orange because max will just give me point 70%. The thing corresponding to 70% is yeah. So is there a notion of decision boundary for regression problems? I guess naively. What is the answer? No. How many said yes? So okay, so there is no decision boundary for.
I think they will be infinite, right?
No, that's like going to philosophy.
Yeah, but of course, even I don't know, but if we can have infinite boundary.
No, so the decision boundary just means the points in the input space. So think of a classification problem. So x's and circles is just those points in the input space, test points potentially, where the probability that it's an x is the same as the probability that it's a circle. So it's 0.5 probability. There's no such notion for regression, right? I mean, probability that y is equal to 0.5 given x is equal to something. It's not clear what it is. Because y is numeric. Okay. So anyway, so that's that. Let's come back to bias and variance. So in the next 19 minutes, so what I want to kind of motivate is three things. Okay. First thing is a picture, so it's easy. So this picture is going to be about EPE. Okay. EPE with all the tau involved there. Okay. And the x-axis is going to be models. Okay. Maybe linear models here. Maybe KNN here. Maybe neural networks of maybe deep neural networks, and so on. And fix some joint distribution, so we don't really some fixed joint distribution between input and output. So there will be a curve like this, which is the training error curve. If you are minimizing residual sum of squares, the more complex the models are, the lesser the better fit you can fit with the training data. Okay, so this doesn't have to be smooth, but something which is decreasing essentially. I just drew it. Something which is decreasing. Okay, this is the training error. Okay. And as you move from I would say simpler models to complex models, your test error will also go down first and go up later. Okay, this is just a I would say illustration. So it's not true that it is always the case for every distribution and every model, every sequence of models here. So this is just an illustration to say that think of the x-axis like models. Simpler model is evaluate like a linear model, best linear model, let's say, has some training error and has some test, or I guess this is the actual EPE. Sorry, this EPE and this is training error. So EPE is nothing but the test error. You just want to know for a model how does it do in the future. In the future, I don't really have to think of a particular data set because I know the joint distribution. I mean, let's say I have a notion of a joint distribution. Then EPE is essentially telling you how well the model scores according to my criteria, whatever it is, right? Residual sum of squares type of, square difference type of criteria, right? So this illustration is trying to point out that there could be models which achieve good training error and good test error, low EPE as well as low training error. But there could be more complex models. You can add more and more parameters. Like think of parameters as a way to think of more complex models. Neural networks may have too many parameters, and linear models have just if there are p features then p parameters and so on. So here you may fit the data really well. So let's go back to this diagram where I said there was a function like this, then linear model will fit it as a line, right? Whereas a neural network may be able to fit the same thing pretty well, right? It can capture all the valleys and hills on that curve, right? This is a feature, one-dimensional feature versus a f of x. Okay, so that's all I mean. So training error is decreasing as you have more complex models to consider. Whereas if you overfit, so this is essentially, so here is where I'm throwing some jargon. Essentially here, there is a big gap between training error and test error. Test error is nothing but the EPE, also called the generalization error. And if you overfit, you may really perform badly. That's what this essentially means. And that's the gap. And that here, you may be underfitting to, in reality, underfitting is essentially that first plot over there. In reality, F true, for example, could be bigly like that. Whereas if you're considering linear models, no matter whichever linear model you consider, it will always have errors. Okay, that big gap between like these errors over here. Okay, and that's why there's a huge training error. And in reality, also you will have a test error also pretty high. Okay, because this dark curve is the true ground truth, let's say. So this is just to kind of boil down the bias and variance derivations that we did in the previous hour. So towards the left side is going to be high bias, a lot of less parameters, high bias, and low variance, compared to the right extreme where there's going to be low bias and high variance. In the sense that if the data changed, for example, this dashed line could correspond to a neural network 1. Okay, if I got another data set, instead of that dashed line, maybe I'll get a different dashed line. Maybe it approximates everywhere else, but maybe at this point it's high variance. Okay, like these dashed lines are too many of them. It's like the variance is going to be high. Okay. So this is a bias variance curve. Yeah.
So in this graph, you have linear models to the left, KNN to the right.
It doesn't have to
just
this illustration.
that will be specific to the particular data we're looking at. Those may be rearranged,
Yes.
right?
Yes. There's a particular data. Yeah. These curves don't have to be exactly like this. Yeah. First of all, even KNN has a choice of K, right? Linear model, at least the ones we've looked at, there's no choice, so there's one model. But with K, we just discussed that when K is large, it should be on this side, closer to the high bias. When K is really small, it should be low bias and high variance. So KNN is not just one model, there's many models. Similarly, many neural networks with different parameters. Similarly, different linear models. So this is just an illustration, like a cartoon.
But it could be that for a linear model also, that the test EP for test could be very high compared to KNN. Could it be like that?
Compared to, yeah, things can switch. I mean, like KNN with k is equal to n, which we said a constant, is a highly biased model compared to a linear model. So maybe if the reality is the constant, then KNN is going to do much better. Yeah. So is this diagram at least clear? Any questions? So really don't have time. So let's figure out how to pick the choice of k. Okay. So there's another topic which is subset selection. I'm going to cover it in the next lecture in conjunction with things called ridge regression and lasso, which are all linear models, so it nicely fits. So for today, to end in the next 10 minutes, I'm going to discuss how to pick the choice of k. Okay, and that's going to be the first strategy, which is going to be completely wrong, is to look at different values of k and see how your training error looks like. Okay, so you can plot training error as a function of k. Okay, and you'll see that training error is going to be something like this, something which increases. Okay. When k is equal to 1, training error is 0. Why is that? What is it? Yeah, because the training data point is its own nearest neighbor. So for every training point, it has its own nearest neighbor. It will correctly tell what the yi is. So for k is equal to 1, it will exactly tell. This is literally 0 error. Okay, and when k increases, it increases, and so this case tells you that k is equal to 1 is a good choice, which is kind of very, it doesn't match with our intuition. So how do we choose k? What we'll do is actually try to estimate EPE. Okay, and this estimation of EPE, this generalization error, is via cross validation. So two important concepts. We can't use training error, so we need to base our choice of k based on something else, which is the EPE. We don't know what the joint distribution between x and y is because we only have data, so we can't directly compute EPE. So we're going to estimate EPE. How do we estimate EPE? We're going to use this cross validation procedure. What is the cross validation procedure is what I'm going to describe right now. But the goal should be clear. The goal is to estimate EPE because I don't know the joint distribution itself. Okay. So cross validation is, think of the training data. Okay, remember this X matrix with the top right mark over there is something like n cross p, right? And there's going to be a corresponding y. Okay, so I'm going to break the data into parts. Okay, in this case, let's say 3 parts. Okay, part 1, part 2, part 3. You can choose any number of parts, but for illustration, I'm going to break the data into 3 parts. So same thing goes here. Okay, this is the first part. This is the third part, and in between is the second part. Okay. So what does cross validation say? So there are 2 words, right? Cross and validate. So first we'll tackle the validation part. So hey, validate. Okay. So what we're going to do is, so we're going to do a procedure for every value of k. So we are trying to figure out the best k value for k and n, right? So pick k is equal to 1, and later on we'll pick k is equal to 2, all the way, some k is equal to 15, let's say. We want to evaluate 15 different choices. I don't know which k I want to pick, so I want to figure out. So pick one of them. Okay, k is fixed. then what we're going to do is use this part 1 and part 2 as our training data set and try to predict the y values of part 3. Okay, that's just called validation. It's just because I was given a training data, which was this whole thing, part 1 and part 2 and part 3, but I myself broke the training data into 3 parts and then separated out a part over which I'm evaluating my performance, which I did not use for my training of my model. Here there is no really training of model, I'm just using that to, because it's KNN. So I'll use part 1, so use part 1 and 2 and predict 3, use 1 and 3 to predict 2, use 2 and 3 to predict 1. Okay, I can do this, right? I can use part 1 and part 2. I have a KNN. I can predict the third part. I know what the true labels are for the third part, which is this guy. And I know what the scoring is. And the scoring I can use residual sum of squares. Or not this, whatever, sum of squares. Okay. So I can get the error on part 3, right? Similarly, I can use 1 and 3 as my training part, over which, basically that's my database over which I'm going to look at the k nearest neighbors, make the prediction on the second part. Okay? That will give me an error for the second part, which I held out. Similarly, I can get an error for the third guy as well. Right? I'm just going to average these errors. Average the errors. Okay? This average is going to be the score for my choice of k is equal to 1. Okay. So this error is nothing but think of it as residual sum of squares, for example. So I picked the choice k is equal to 1. I broke my data set into 3 parts. I use the first 2 parts to make the prediction on the third part. That gives me the first error, first line, that error. Use the first and the third parts to predict on the second guy. That gives me error for just the second guy predictions. Similarly, I use 2 and 3 to predict the first guy. That gives me errors on the for predicting on the first chunk, right? Each chunk is called a fold, and I can average those errors, and that's my score, average performance of k is equal to 1. Okay. I can repeat this whole thing for every k, pick the k which has the lowest value. This score that I have averaged is an estimate for EPE. So remember this expected square prediction error. The score here is an estimate for that. Remember, the whole point of doing cross-validation is because we can't use training data reliably. So we have to estimate EPE. And to do that, this is the cross-validation procedure. This is essentially what it is. For every choice that you have, 15 choices in this example, right? 15 choices. For each choice, break your data. First of all, break your data set into folds. In this example, I'm doing it in 3 folds. You can think of how to do it for many more folds, but 3 is enough. Okay. For every choice, for every fold, pick the other 2 folds of the training data, make predictions on that fold. That's those 3, because the 3 folds, I make predictions on 3 different folds. By keeping them outside, everything else as my training data. Get the errors, average them. That's my score for this choice. For every choice, I can make a score and pick the choice which has the lowest score, because these scores are my proxy for expected square prediction error. Okay. Yeah.
And you use the RSS to determine the error there. But
Yeah, you can use anything.
There
Yeah.
are several. You can use different methods, right?
Yes. So then it will not be expected square prediction error. It will be what, and the expectation should correspond to the, like if you use squared error, yi minus f of xi squared, then your EPE will be, y minus f of x squares, right? Something like this. Here you can choose, you can change you can change that. This is the general template, holds for any other model choice, but for KNN, this is the way. Yeah.
Practically speaking, it's not a good idea to start with K1 at this point, right? Because your
Why not?
average is going to be.
No.
Well, if you choose K1 as we've seen in the previous example.
Yeah, this will not be low, because you did not use. So try to make a. So if you use k is equal to 1, let's say you're using 1 and 2 to predict the third part. Third part's, you're making prediction on third part. So for every third part's x value, you're saying who are the neighbors. Even if k is equal to 1, there will not be the nearest point to that guy could be far away. So you could be off. So you'll not get a zero training error here. So k is equal to 1, it gets rid of that issue that we had with the training data. Okay. So this should hopefully be consistent with cross-validation that some of you have seen in another class, right? If there is a difference, point it out right now. Yeah.
Actually, how does this apply if I'm doing a linear model?
We will get to linear model tomorrow because so far in our linear model there was no choice. We were literally, beta hat is just x transpose x, the whole inverse, x transpose y, something to do with data, and there was no choice that you had. But next class we'll see that there are some choices that we can bring in to further, tweak this bias variance trade-off. But so far, no linear model here. Okay, this is the way you can pick the right k. Any questions? Yeah. Yeah. So actually, last time I did not even record, although the thing was on. So I hope it's recording. If it is recording, I can send it to you guys. This is just experimental. If it records, then I'll send it to you. Yeah.
Cross validation. Because you are running the algorithm against the basis data.
Yeah.
You're kind of showing all the data to the algorithm.
It's going to be biased. Yeah.
Don't you think that this is not the right approach basically because you should never just touch your testing data set, right?
There is no testing data set here. That's my whole training data.
Yeah, but if it's not it, how will you come to know the choice of the game?
Okay, why don't you come over here? We'll discuss. Okay, thank you. Oh yeah, return the answer scripts.